In this video, we're going to work on section 5.7, the natural logarithmic function, integration. And we're going to learn how to use the log rule to integrate a rational function and integrate trigonometric functions. Now let's think back to the log rule for differentiation. The derivative of the natural log was 1 over x. The natural log of x was 1 over x. The derivative of the natural log of u, and remember u is some inner function. That derivative is, our denominator is u, this function, and its numerator is u primed. Sort of like, what is the derivative of the ln of x to the third? Well, that derivative, our denominator is going to be our function x to the third, and our numerator would be its derivative, 3x squared. Now, if we think in reverse, we know the integration rules for log functions. So we let u be a differentiable function of x. And here's the most basic one. We have our antiderivative of 1 over x dx, and that antiderivative is the natural log of the absolute value of x plus c. Remember, the natural log function only has positive values in its domain. So we have to make sure the absolute value bars are around the x. If we have a more complex function, a composite function, the antiderivative of 1 over u du is going to be the natural log of the absolute value of that inner function u plus c. Because du equals u prime dx, the second formula can also be written like this. The antiderivative of u prime over u dx. And we just do the integration, and it's the natural log of the bottom, the natural log of the absolute value of u plus c. So here's a very simple example 1 using the log rule for integration. We have the antiderivative of 2 over x dx. And if you want to think about this step by step, the 2 up top is a constant multiple. We can take that out in front of the antiderivative sign, and we're left with 1 over x dx. So we have it in the format. The antiderivative of 1 over x is the ln of that denominator, absolute value, 2 times the ln of x plus c. And if we wanted to use the rules of exponents, remember we can move this 2 up top. The ln of x squared. And now that it's squared, we can drop the absolute value bars, because no matter what x is, positive or negative, if we square it, the result will be positive. And we got to add our constant, c. ln of x squared plus c. Example 2 is also going to need a little tweak, inside and outside of our integration sign. And we could even think about, let's do this one with a u substitution. We're going to let u equal our denominator, 4x minus 1. So du dx is going to be 4. And multiply both sides by dx. Du equals 4 dx. Well, we don't have a 4 there. We're missing it. We could either think about, squeezing it right in there, or we could put it up on top. And, let's just put that up on top here. And if we go back to that first slide, when it's a more complicated function, remember we want to get it into the format, into the setup of our denominator is a function, its numerator is the denominator's derivative. And that's just what we have here. Our denominator is 4x minus 1, and our numerator is that function's derivative. But let's continue with our u sub, and we put a 4 here to the right of the integral sign. We have to balance it with a 1/4 out in front. So we have 1/4, the antiderivative, and our 4 dx is our du, and then we have 1 over u. So we've completed our u substitution. Let's take the antiderivative. That is 1/4. We'll have the natural log of the absolute value of our denominator plus c. And now that we're almost done here, let's do our u substitution back in. So that'll be the ln of our u is 4x minus 1, absolute value, plus c. Example 3, we're going to find area with the log rule. Remember, the function, to be considered finding area under a curve, our function has to be positive across the interval. And here we're looking at the area between the x-axis, the curve, and the line x equals 3. So here's our line x equals 3. The function is positive across that area, or that interval, so we are looking at area underneath the curve. So let's set up our antiderivative. They didn't really give it to us on this one, but they gave us everything we need. We want the definite integral from 0 to 3, and we can get that from the setup information or from the picture here. Our function is x divided by x squared plus 1 dx. So let's let u equal our denominator. U is going to equal x squared plus 1. And then du will equal 2x dx. And we have x dx. We're just missing that constant 2. So we can put a 2 here with the x and a 1/2 out front of the integral to balance it out. And now we're ready to do the u substitution. So we're going to have 1/2 our definite integral from 0 to 3 of u prime over u. And let's see, should we run our limits through the u substitution and then just integrate with respect to u? We'll just leave them as is and substitute back in and apply the fundamental theorem of calculus. So when we take the antiderivative, we're going to have 1/2 of the ln of the absolute value of u, or x squared plus 1, plus c. Ooh, that's right, this is the definite integral, no plus c. We have our bracket, and we're going from 0 to 3. So we run our upper and lower limits through the function. First we plug in our 3 for x, so we're going to have 1/2 the ln of 3 squared is 9, plus 1 is 10, ln of 10. And then minus, plug in our lower limit of 0. The ln of 0 squared plus 1 is 1. And the ln of 1, that should be something we have committed to memory. We have our ln of 10. The ln of 1 is 0. Remember, the exponential functions cross the y-axis at 0, 1, and they go up. And the natural log function crosses at 1, 0, like so. So the ln of an x value of 1 is 0. So we have 1/2 the ln of 10. And if you punch that into your calculator, you could get the approximation, approximately 1.151. Now in example 4 here, this is to recognize the quotient forms of the log rule. Remember, we want to set it up so we have a function as our denominator, and our numerator is its derivative. And we can do some of these with the u sub and some without. If I look at the first one here, letter A, my denominator is x to the third plus x. The derivative of that would be 3x squared plus 1. So we are all ready to go. If we did want to do a u sub, that would be the antiderivative of u prime over u du. So we can just apply the theorem from earlier in the video, and we're going to have this antiderivative is the ln of the absolute value of our denominator, x squared, or x to the third plus x, absolute value, plus c. In the second one, we have the antiderivative. Here's some trig functions. Always look at the denominator. Our denominator here is tangent. If we let u equal tan, then du equals, what's the derivative of tangent? Secant squared. And of course, that just happens to be our denominator, or our numerator. So we are set up for u prime over u du. So our antiderivative is going to be the natural log of the absolute value of our denominator, the ln of the absolute value of tan, plus our constant c. Letter C here looks like it might need some tweaking. So let's write this one out a little more formally with the u substitution. If we let u equal our denominator, x squared plus 2x, our derivative du is going to be 2x plus 2 dx. So we're close. Here we have our antiderivative sign. Our numerator is x plus 1, and we need 2x plus 2. So we're an easy fix away. What we would need to do is have a 2 up top, and when we distributed it, it would be 2x plus 2, just like we needed. So to put a 2 to the right of the antiderivative sign, we're going to have to balance it with a 1/2. So when we take the antiderivative, it's going to be 1/2 the natural log of the absolute value of that denominator plus c. And letter D. Let's see what's going on here. If we let u equal our denominator, 3x plus 2, our derivative, du, would be 3 dx. And we don't have a 3 dx. We need to tweak this here with a 3 to the right of the integral sign and a 1/3 to balance it to the left. And then we are ready to integrate. Our denominator is a function. Our numerator is that function's derivative. So we will have 1/3 the natural log of the absolute value of 3x plus 2 plus our arbitrary constant. So remember, just look, denominator is a function, the numerator is its derivative, or you might just be a constant away from that being its derivative. That fits our natural log format, and we can easily integrate with our natural log integration rules. Integrals to which the log rule can be applied often appear in a disguised form. For instance, if a rational function has a numerator of a degree greater than or equal to that of the denominator, division may reveal a form which you can apply the log rule. And this is shown here in example 5. So when we look at this, our denominator is x squared plus 1. If we take the derivative, that would be 2x, and our numerator is a far cry away from being 2x. So we're going to have to try something else. And remember, a ratio like this, it is a division problem. So let's come over here, do a little scratch work, and do some good old long division. We're going to take x squared plus 1, and we are going to divide that into x squared plus x plus 1. X squared plus x plus 1. So I need something up here times x squared is equal to x squared. Well, that's going to be a 1. And let me switch to red here. So we do a 1. 1 times x squared is x squared. And then 1 times 1 is 1. Now remember, when we're doing this long division, we are subtracting. So I'm imagining parentheses around here. I'm going to distribute a negative and sort of add then. So I distribute the negative and add here, I will get a 0. I'll distribute my negative here, and when I add, I'll have x minus negative 0, or just plain old x. And then I distribute my negative here, and I'll have 1 and negative 1, and when I add those, I will get 0. So that is my remainder. When I do this division, I come up with 1 plus my remainder x over top of my divisor, x squared plus 1. So I can rewrite my integral. This I couldn't do much with, but it is the same as the antiderivative of 1 plus x over x squared plus 1. And to make this a little easier to see what's going on, we can break this into 2 separate integrals. We can have the antiderivative of 1 plus the antiderivative of x over x squared plus 1. And I should have a little dx in there and another little dx. So let's look at this second piece. My denominator is x squared plus 1. My numerator, or the derivative of that, would be 2x. So I need to tweak this. I need a 2x dx for my du, and I'll balance that with a 1/2. And now we're ready to integrate. So when we take the antiderivative of the constant 1 with respect to x, we get an x plus. Here we'll have 1/2. And now this is all set up in the format of u prime over u, function on the bottom, derivative up top. So it's going to be the natural log of the absolute value of its denominator plus c. You know, technically when we integrated the first piece, there would be a plus c. We integrate the second piece, there's a plus c. But an arbitrary constant plus another arbitrary constant is just another arbitrary constant. So we're left with x plus 1/2, the ln of that quantity. Now the next example presents another instance in which the use of the log rule is disguised. In this case, a change of variables is going to help us recognize, that the log rule is applicable. So if I look at my denominator here, it's x plus 1 quantity squared. If I let what is within the parentheses be my u, I will have u equals x plus 1. And then my du, dx, would be equal to 1, and then multiply both sides by dx. Du is equal to dx. So let's start substituting some stuff in here and see what we have. We have our antiderivative sign. This 2 is a constant multiple. We can pull that out front. So we're going to have a 2, and then up top we have an x over our u squared. So we're going to have an x over u squared dx. Du and dx are interchangeable, so I can take this dx away and put in a du right now. But this x is a little something extra that we don't see what to do with right now. In the previous section with integration by substitution, we can go back to our u substitution here. We can solve this for x in terms of u and plug it in for that x. So if I come back up here, x is an easy fix. X is going to equal u minus 1. So I can replace this x with a u minus 1. And let's see what that looks like when we make that switch. So we have 2, our antiderivative. We're going to replace that u up or x up top with a u minus 1 over u squared. Doesn't look much better, but our numerator is 2 terms. Our denominator is a single term. When we were taking derivatives, a good strategy is to bust that up into separate fractions and see if anything simplifies. So we're going to have a first piece of our numerator over our denominator minus the second piece of our numerator over that same denominator, and each of these would and then we'd have a du for both of them. Now let's see, that first piece, u over u squared, that can simplify. And also, maybe to make this easier to see, let's break this apart into 2 separate integrals. So we're going to have 2, and the antiderivative of this simplified will be 1 over u du, and we could write that as just du over u, or u prime over u. So let's do that. U prime over u minus, we're going to have 2, and the antiderivative of 1 over u squared is u to the negative 2 du. Now we have a piece of it that looks like it fits the integration for logarithms, and we have this other piece here that we will not need to use our log integration on. So here we're going to have 2. Here we are in the format u prime over u. So when we take that antiderivative, it will be the ln of the absolute value of u minus, and then we'll have 2. This will just be straight up power rule. It will raise the power by 1. So it'll be u to the negative 1 power and divide by the new power negative 1, which would change this to a plus. And then for each of these we would have a plus c. And our last step, let's plug our u value back in. So we have 2 ln of the absolute value of x plus 1 plus we have 2u to the negative 1, and that negative 1 will drop us to the denominator. So down in the denominator, it will be the quantity x plus 1 to the first power, which we don't have to write on there. And we throw on our plus c, our arbitrary constant. 2 ln of that quantity x plus 1 absolute value plus 2 over x plus 1 quantity plus c. So as you study the methods shown in these last two examples, be aware that both methods involve rewriting a disguised integrand so that it fits one or more of the basic integration formulas. Throughout the remaining sections of this chapter and into chapter that will be 9 in our book, much time is devoted to integration techniques. Most all of Calculus 2 in college is integration. To master these techniques, you must recognize the form-fitting nature of integration. In this sense, integration is not nearly straightforward as differentiation. Differentiation takes the form of, here's the question, what's the answer? Integration is more like, here's the answer, what was the question? And we have some following guidelines here to use for integration. First, learn a basic list of integration formulas, including those given in this section. You now have 12 of them. The power rule, the log rule, the 10 trig rules, and by the end of section in our book, it'll be 6, 7. This list will have expanded to over 20 basic rules. Find an integration formula that resembles all or part of the integrand, and by trial and error, find a choice of u that will make the integrand conform to the formula. If you cannot find a u substitution that works, try altering the integrand. You might try a trig identity, multiplying and dividing by the same quantity, adding and subtracting of the same quantity, or long division. Be creative. If you have access to computer software that will find antiderivatives symbolically, by all means use it.